Hello there, Mr. Sutton here, bringing you the AB Calculus 6-2 Extra Practice Number 4 solutions on separable differential equations. On this problem, I'm trying to find the particular solution for this differential equation. So one thing I notice is that I have an output variable, y, in the differential equation. So I'm going to have to separate my variables on this one, which basically means I need to get the y to be with the dy and the dx to be with, well, everything else. So let me start by multiplying both sides by secant squared of y. So I have that plus the dy over there. And then there's nothing except for the 1 on the right side, so I'll just multiply the dx to be with that. Taking the antiderivative of each side now, antiderivative of secant squared of y is going to be tan of y. And then for this 1 dx here, that's going to become an x plus c on the right side. To find the c value, we have to plug in our initial condition. So I've got tan of 0, because that was the output there, equals input of 3 plus c. So this means that, let's see, tan of 0 is just 0. Subtracting 3, we have c equals negative 3. And then plugging that back in, I can write tan of y equals x minus 3. But the game's not over until y is completely isolated, so we just have to take the arctan of both sides, giving us y equals arctan of x minus 3. For this differential equation, we notice that there's an output variable, y, in the differential equation, so we're going to have to separate variables before we take antiderivatives on this one. So let me multiply by y to get it over with the dy. And then I'm going to multiply by dx to get it over with everything else. It's nice that there's an x over there, but we didn't need one. We just wanted to get rid of the dx over there. So taking the antiderivative of each side, we have 1/2 y squared on the left side. On the right side, this is going to become an x squared, and we'll also put the plus c over there on the right side. Now to get the value of c, I have to plug in my initial condition. So I'm going to have 1/2 times the y value negative 3 squared on the left side. On the right side, I've got the x value negative 2 being squared, and we have a plus c still over there. So back on the left, this is 9 over 2. On the right side, we have 4 plus c. So to find c, you basically have to do 9 over 2 minus 4, or 9 over 2 minus 8 over 2, which is 1 over 2. So that's going to be our c value. And now let's put that c value back in here in this equation. So here's where we stand, and we're getting there, but it's not over till y is completely isolated. So next step, let me multiply everything by 2 to get rid of that 1/2. So I've got y squared equals 2x squared plus 1. And at this point, I'm going to need to take the square root of both sides. Now when you do this, you get a plus or minus root. However, you're only allowed to use one of those for your particular solution. So to figure out which one, we have to look at the initial condition, where we see that the y value that comes out of all this is negative. If y is negative 3, then in general, y is supposed to be negative. So if I have to choose between y equals a plus or a minus, I'm going to go with y equals negative, and then it's going to be negative square root of 2x squared plus 1. For this problem, we're trying to find the particular solution for this differential equation. Since I have an output variable, y, in the differential equation, I need to separate variables on this one and get the y to be with the dy. So I can do that by multiplying both sides by y squared. So I have y squared dy on the left side of the equation. And I'll multiply by dx as well to get it on the other side. So that's x dx over on the right. Now to take the antiderivative on the left side, this is going to be, let's see, this bumps up to a 3. So this is 1/3 y cubed. On the right side, this is going to be 1/2 x squared plus c. We still need to find the c value though, so we're going to plug in the initial condition to do that. So I have 1/3 times the y value cube root of 36 over 2, all of that cubed. So that's kind of a crazy one, and we have a 1/3 out there as well. There we go. And on the right side, we have 1/2 times the x value negative 1 being squared, and then we have the plus c as well. So let's see here. This is just 1/2 plus c on the right side. On the left side, a little more complicated. So we have to cube both of these things. We have to cube the numerator and denominator separately. So that's going to give us 36 in the numerator and 2 cubed, which is 8 in the denominator. So that's 36 over 8 times 1 over 3. 36 divided by 3 is 12, so this is really 12 over 8 on the left side. But hold on a sec, 12 over 8 is really just 3 over 2. So when the dust settles, we have 3 over 2 equals 1/2 plus c. Subtracting the 1/2, we just get 2 over 2, which is just 1. After all that, c equals 1. So plugging that back in up here, we have 1/3 y cubed equals 1/2 x squared plus 1. But we're not done until we isolate y, so let's multiply everything by 3. That's going to be 3/2 x squared plus 3. And then we have to take the cube root of both sides. And when you take the cube root, there's no plus or minus, so we don't have to worry about that. This is just going to be y equals cube root of all the stuff over there. And we are done. On this problem, I want the particular solution to this differential equation with the initial condition given here. So there's a lot going on the right side here. The thing that really catches my interest, though, is this y over here. We have an output variable in our differential equation, which tells me that I need to use separation of variables here. So I'm going to have to divide this y by both sides by this y to get it over with the dy. So that'll give me y to the negative 1 dy on the left side of my equation now. And I'm going to multiply both sides by dx to get it over with the x's on the right. So we have 2x dx over x squared plus 1. And at this point, it's time to take some antiderivatives. Before I do that, though, actually, this is just kind of a mess over on the right side. I'm actually going to have to do a little more work to take the antiderivative over here. It's not a one-step antiderivative. But one thing I do notice, you can think of this x squared plus 1 as kind of like an inner function. And the important thing about this is that the derivative of x squared plus 1, which involves an x, is elsewhere in the problem. So this would be a good time to use integration by substitution. So let me let u equal x squared plus 1, and then du equals 2x dx, which means that I can rewrite dx as du over 2x. Plugging all that back in, we have, let's see here, 2x over u, and we also have a du over 2x. 2x's cancel, so we really just end up with du over u. And now I can go ahead and take the antiderivative. On the left side, it'll be with respect to y. On the right side, I'm taking the antiderivative with respect to u. So on the left side, this is going to be ln absolute value of y. And on the right side, it's actually the same kind of situation, just written in fraction form instead of with a negative exponent. This is going to be ln absolute value of u. Don't forget we have a plus c over there, though. And one more step I'm going to do before I find the value of c, just to make my life a little bit easier. I'm going to go back and replace the u with the x squared plus 1, just because my initial condition has an x value. And if I don't want to have to convert that to a u value, I might as well just make this all in terms of x. Besides, it's not really that nasty to look at, right? And also, I am going to have to come up with the particular solution at some point, which is going to need to have an x in it instead of a u. So, at this point, let's find the c value. I'm going to plug in negative 2 for the y over here. So that's ln of negative 2. And in here, I have ln of, let's see, we have negative 1 squared plus 1 inside the absolute value, plus c. This is ln of positive 2 on the left side. On the right side, this is ln of positive 2 plus c. Subtracting ln of 2 from both sides, we just end up with c equals 0. And now I'm going to go ahead and plug that back into this differential, or this general solution. Now, before I do this, I need to resolve these absolute values. Looking at my initial condition, I notice that y in the initial condition is negative 2. Well, if y is negative 2, that means that this expression inside absolute value, which happens to itself just be y, is going to be negative. So that means I have to rewrite this without the absolute value as ln of negative y, just to make sure that I'm not taking the ln of a negative number. And I also have to resolve the absolute value with the x squared plus 1 in it. Now, since my initial x value is 1, that means x squared plus 1 is going to come out positive. In fact, x squared plus 1 comes out positive no matter what you plug into it. So that means that I can replace this absolute value with just regular parentheses. I don't have to negate anything. So I have ln of just parentheses x squared plus 1. And plus c is just a plus 0, so we don't have to write anything there. So now I can raise e to both sides. That gives me negative y equals x squared plus 1. And just multiplying by negative 1 to get y truly isolated, we have y equals negative x squared minus 1. For this problem, I have this differential equation with this initial condition which actually the initial condition looks even worse than the differential equation. But we're going to go ahead and find the particular solution for this thing anyway. So one thing I notice is that we have a y in our differential equation. So that means we have to separate our variables in the very beginning. So I need to get the y squared over with the dy. I can do that by multiplying it by both sides. So y squared dy on the left side. And then let me move the dx over with the x's. So I'll have 2e to the x dx if I multiply both sides by dx. At this point, I can go ahead and take the antiderivative for both sides. So on the left side, I've got 1/3 y to the third power. On the right side, this is going to be easy. This is just 2e to the x. Don't forget the plus c, though. And at this point, this is where it gets a little bit crazy. I have to plug in the initial condition here in order to figure out the value of c. Well, here we go. So for the y value I'm plugging in, it's this whole weird radical fraction thing. So I have 1/3 this craziness cubed, which we're going to have to take in a few steps. I'm not going to try to do all of that in my head. On the right side, we have the much more manageable 2e to the negative 2 plus c, just plugging in the x value from the initial condition. So back to the left side now. We're going to take this in a couple bites here. So first thing I'm going to do is cube the numerator and denominator. That's going to give me just 3e cubed plus 6e in the numerator. And we're going to have e cubed in the denominator. And while I'm at it, let me just multiply this 1/3 to get a 3 down in the denominator. And now I'm going to simplify a little bit here. I can divide the numerator, both terms there, by 3e cubed. 3e cubed over itself is just 1. 6e over 3e cubed, that's going to be 2e to the negative 2. So we have 1 plus 2e to the negative 2 equals 2e to the negative 2 plus c. Well, you can see here these 2e to the negative 2's are going to cancel when I subtract from both sides. So then we just end up with c equals 1 after all that. All right, so I can plug that one back into this equation right here to get 1/3 y cubed equals 2e to the x plus 1. And then don't forget to isolate y. So I'll multiply both sides by 3. That's going to be 6e to the x plus 3 on the right. And to get y by itself, I have to cube root both sides. So y then is just going to be the cube root of 6e to the x plus 3. For this problem, I'm trying to solve a differential equation for the particular solution. So let me start by noticing that I have a y in the differential equation, so I'm going to separate my variables. I'll multiply y by both sides to get it with the dy, and then to get rid of this dx, I'm going to multiply it to the other side to be with the 2x. Next, time for the antiderivative on each side. So that's 1/2 y squared on the left, and this is going to be x squared plus c on the right side. Now I have to plug in my initial condition to get the c value. So I have 1/2 times the y value negative radical 3 squared equals, we have an x value of 1 being squared plus a c. So this is going to be, let's see, 1/2 times just 3, so 3/2. We have a 1 on the right. 3/2 minus 1 gives us a c value of 1/2. Plugging that back in up here, I get this equation right here. Now I have to isolate the y value. So that's going to be, let's see, multiply everything by 2. We have 2x squared plus 1. And at this point, I have to take the square root of both sides. Now be careful, because when you square root, you get a plus and a minus root. And we have to pick just one of those for the particular solution. You can't have both. So looking at my initial condition, I see the y value up here, negative radical 3, is just in general negative. So that means I have to write y equals something negative. So in this case, we're going to have y equals negative radical 2x squared plus 1. For this free response problem, we have a coffee pot in the shape of a cylinder with a radius of 5 inches, which were shown here. H is the depth of the coffee in the pot, measured in inches, and it's a function of time in seconds. Volume is changing at the rate of negative 5 pi radical h cubic inches per second. Don't ask how they know that. And they even give us the volume formula for a cylinder, pi r squared h, going back to our MCAS formula sheet days. So for our first task on this problem, we just have to show that dH over dt has a value of negative radical h over 5. Okay, well, it would help if we had some kind of equation that had an h in it. We actually do. We have this volume equation here, but now we're talking about a rate of change for h. That's what this is talking about, the rate at which h is changing with respect to time. We also have a rate of change for volume, because they told us that the coffee pot was changing, the volume was changing at a rate of negative 5 pi radical h cubic inches per second. If we have multiple rates in here, we have a related rates kind of situation, so we have to take this formula that ties everything together and differentiate it implicitly with respect to time. So everything is going to get a d letter over dt kind of tail. Now before we do any of that craziness, we can make our lives a little bit easier, because we already know what the radius is. The radius is going to be a constant value of 5, because this is a coffee pot. It's not changing shape. It's going to stay a cylinder. It's going to be a cylinder of the same radius no matter how much coffee you put in it. So when we rewrite this equation here, I'm going to write this with 5 plugged in for r, and that's going to make our lives a whole lot easier. So then we can say volume is really just 25 pi h. And now this is what I'm going to take the derivative of with respect to time. So derivative of v is going to be dv over dt. And over here I'm going to have 25 pi dh over dt. Everything gets multiplied by the derivative of itself with respect to time. All right, well, I'm getting there. I can go a little bit further, though. At some point, I only want to have dh over dt left over, because they wanted us to show that dH over dt equaled something. So now this dV over dt needs to get replaced with something. We can replace it with this negative 5 pi radical h expression, they said, because this is the rate at which the volume of our coffee pot is changing. So I'll plug that in for dV over dt. And at this point, all we have to do is divide to get dH over dt by itself. So the pi's are going to cancel. We have a negative 5 over 25, which comes out to negative 1 over 5. So then we just have dH over dt equals negative radical h over 5. For this part of the problem, they want us to solve the differential equation dH over dt equals negative radical h over 5 for h as a function of t. So this is a diff-EQ situation. And there's a little bit more going on here. We have to be careful. Notice that the h, which is the output variable here, is in the differential equation. So that means we have to use separation of variables, or specifically we need to get the h to be with the dh. So to do that, I'm going to divide both sides by radical h, which is going to give me an h to the negative 1/2 power over on the left side of the equation. And I'll also move the 5 over there as well. Why not? So I'll have a 5h to the negative 1/2 dh. And on the right side, I still have a negative 1, so I'm going to have a negative 1 dt if I multiply dt by both sides. So taking my antiderivative now, on the left side, using the reverse power rule, this is going to bump up to a 1/2. And then dividing by 1/2, I'm actually multiplying by 2, so this is going to be 10h to the 1/2 power on the left side. On the right side, just using my reverse line rule, this is going to be negative 1t plus c. Can't forget my constant of integration. And to find the c value, I have to plug in the initial condition. Well, what's that? They said that h equals 17 at time 0. So I'm going to plug 17 in for the h here, and that's going to equal negative 0 plus c. So this means c just equals whatever the stuff on the left equals, which is, I guess you could write that as 10 radical 17 if you want to be fancy about it. Plugging c back in up here, we have 10h to the 1/2 equals negative t plus 10 radical 17. And now I have to isolate h. So divide both sides by 10. That's negative 1/10 t plus just radical 17. And then finally, we just have to square both sides. So we have h equals all the stuff over here on the right inside a big old squared parentheses. And we are done. For this last part of the problem, I just want to know at what time is the coffee pot empty? Well, if the coffee pot is empty, what does that mean? It means a few things. It means the volume is 0. It also means that the depth of the coffee, h, has to be 0. And that last piece is important because on the end of part B, we ended up with a function here, just to review part B. Here's this function h equals something with time plugged in. So we have a function for the height of the coffee in the cup, or the cylinder. We want this h value to be 0. If there's no coffee left, the depth is going to be 0. So we're just going to take all this stuff that h equals and set it equal to 0. Now we just have to solve for t. So we can start by square rooting both sides. Square root of 0 is just 0. So that works out nicely. And then I'm just going to subtract radical 17 and multiply by negative 10. So that's just going to be 10 radical 17. And this is going to be measured in seconds because this is time for this problem.